Hello everyone. So I welcome you in this lecture and today we are going to talk about dynamic programming. Dynamic programming is a very powerful technique of algorithm design. Many of the problems are solved using dynamic programming and it provides a very efficient running time. Most of the problems that we are solving with dynamic programming are optimization problems. So in this lecture we are going to talk about the fundamentals of dynamic programming and also we will look to the some problem areas or some problems where this approach can be applicable. So let's start. So let us first read that how dynamic programming can be defined. So it is a general algorithm design technique for solving problem defined by or formulated as a recurrence with overlapping subinstances. So one of the key requirement of any problem that can be solved by dynamic programming is the problem must be represented using a recursive, means you are able to represent your problem recursively, or you must be able to define a recurrence for the problem. Then the problem can be solved by dynamic programming. Or in the other way we can say, if we are able to represent our problem into sub problems, and these sub problems must be of repeating nature, they must not be extending. So if you find any problem and we are able to represent the problem into sub problems where sub problems are of repeating nature, then the problem will be very much suitable for solving by dynamic programming. We will discuss in the later slides there we have some problems. If we solve it, the say problem without using a dynamic approach, the running time may go up to exponential. It may be up to 2 raised to power n. But the same problem may be solved by dynamic programming approach, then it can be reduced to linear. So 2 power n problem can be reduced to n or n square, and both the running time is actually much better than this 2 power n. So let us see that when it is evolved, who proposed this approach. So this is proposed in the 1950 by American mathematician Richard Bellman to solve the optimization problem. So he proposed the name dynamic programming. The idea of keeping the word dynamic here is actually he was given the name dynamic to make it more interesting and giving a fresh feeling. The other purpose of giving the name dynamic is here we are solving the problem and during the runtime. So whenever we use the term runtime is also used. Word is also used in synonym with the dynamic. So during the runtime, at the time of solving the problem, we store the intermediate results, and these intermediate results are actually used to get the optimal solution. So the key idea is to store the intermediate results. The second term is programming. So programming here doesn't means any code or writing any instructions code, but here it means the planning. So dynamic programming means actually that while solving a problem, so during the runtime when you are getting the intermediate results, so you need to plan in such a way so that these intermediate results can be used to get your final solution. And if we go with this approach, we will be getting the optimal solution. So the main idea of this approach is set up a recurrence relating to a solution to a larger instance to a solution of some smaller instance. So here we want to make one recurrence of a solution of a larger instance to a solution of a smaller instance. That means here we are focusing to define our problem into sub problems, and then we will be trying to solve each of these sub problems optimally, and assuming that these optimal solutions at the end will give us a final optimal solution of the given problem. So our main focus is to solve these smaller instances once, and then after solving these smaller instances, keep these instances results in one memory area. So we are calling it as so we are taking as a table here. So we will create one table at runtime, and in this table we will be storing these intermediate results. extract solution to the initial instance from the table. And we believe that because these instances are repeating, so whenever we keep on solving our these instances that comes during the process of solving our problem, we keep on referring these answers which are already stored to get the final answer. The approach basically says that because we have already discussed that here the sub problems are keep on repeating, so once you solve any sub problems, then there is no need to solve it again, but we will directly use the result which is stored in the given table. So let us see some more properties of dynamic programming, and then we will take one example to understand in a better way. Now the framework to solve the optimization problem. So the key idea of dynamic programming is to solve the optimization problem. So when Wellman proposed this approach, he was actually interested to propose a solution to solve the optimization problems. Now optimization problems are basically represented using any objective functions, and our objective is to either minimize this objective function or maximize this objective function. For example, you may think about purchasing the most valuable thing with a defined given budget to you. So we want to make use of the given budget to us, or we want to move from one state to another state with the minimum effort or with the minimum cost, or you might be wondering to come up with the architecture, or if you're planning a city in such a way so that you need to identify that how many hospitals must be constructed at which location so that it can be accessible to maximum citizens of that locality. So these are different areas of optimization problem. So normally when we talk about optimization problems, the key areas are like signal processing. The other area where we talk about optimization problem is operation research. Operation research basically tells you or teaches you the different techniques of solving the optimization problems. Then we have area of soft computing. We have area called computational intelligence, computational biology, geometry. So we have various areas where we actually talk about optimization problems, and these optimization problems can be easily solved using a dynamic programming. Now what actually the approach here in the dynamic programming is, for each current choice determine what subproblems could remain if this choice were made. Already we have discussed that the problem to be solved into in a steps, and it is consisting of subproblems. So at every step when you are deciding the solution for a subproblem, you need to check that what will it cost if you choose a particular solution for it. So when we talk about dynamic programming, here we are using some heuristics that guide us that how to move while solving the problem. So recursively find the optimal cost of those subproblems. So it is not a greedy approach where we only considered about the local scenario, but here we have to look to the global scenario. We have to look into the overall impact of choosing the solution for any subproblems. So definitely we must have to use some heuristics here, combining those costs with the cost of the current choice itself to obtain an overall cost for this choice. So at every step you might be having multiple choice to proceed. So while selecting any choice at any stage, you need to um, look at the cost of a choice that you want to choose, and you have to add the cost of the current choice with the cost of the existing um, with the cost of already selected choices in order to identify the total cost at any point of time. So definitely this can be done with the help of any provision that is associated with the problem, and we call this provision as a heuristics. So heuristics is actually a kind of a function or a provision that help you to identify that which of the available choices will be good for you to reach to the optimal solution. Select a current choice that produces the minimal overall cost. So this is the approach of the uh, dynamic programming. So let's move to the next part. So let us look about some elements of dynamic programming, or you can say the approach of solving a problem. So constructing a solution to a problem by building it up dynamically from solution to smaller sub problems. So dynamic programming is basically a bottom up approach. So in the bottom approach, what we do, we generally solve a very smallest part of the problem, or you can say any sub problem, and then we combine all these small problem to get the answer of the larger problem. So this is the approach that we uh, follow in dynamic programming, and this is why we call it as a bottom up approach. Principle of optimality. So when we talk about dynamic programming, it reflects the principle of optimality. So the principle of optimality means that we believe that if we are defining a problem consisting of n1, n2, n3, n4 subproblems, and if we solve each of these subproblems optimally, then the entire solution will also be optimal. So the optimality principle says that the solution that every optimal solution for the subinstances will give you the final optimal solution. And then the main and the important concept that we use in the dynamic programming is memoization. Now, memoization is only meaningful when we have overlapping subproblems. Overlapping subproblem is the problems which are repeated. So, if you are having a problem and which has n subproblems, then these n subproblems must not be of different kind, but most of them must be of overlapping nature. Most of them must be of repeated nature. Then only this technique will be useful. Now, the advantage of this memoization is it avoids calculating the same thing twice. So, memoization is basically referring to storing your intermediate results. The benefit of storing these intermediate results is because we are having a repeated sub problem. So once you solve any problem, after doing some effort, you will keep the result in some memory area, so that later when the same problem will be repeated, there is no need to put again the same effort. Rather than we can simply use the result and proceed. Usually by keeping a table of no results that fill up as a substances are solved. So memoization basically refers that in this dynamic programming approach, we usually reserve one memory space. We are calling it as one table, you can say, where we keep on storing the results that we are getting as an intermediate effort. And whenever the same kind of effort is required, we avoid doing the same effort, but we simply use the result and proceed. So this is how our overall time will reduce. So let us look up to some problem areas where the dynamic programming algorithms are used to compute the binomial coefficient. Again, the dynamic programming approach is very helpful here. Finding the longest common subsequence. So you are provided two set of data, or you can say two different strings, and we are looking for the common subsequence between these two. So for this, again, dynamic programming is very helpful. To find the transitive closure. So transitive closure basically defines the complete information in the graph about the path between the two vertices, and this can be find out by using a Washer algorithm. Then we have all pair shortest path. Already we have discussed in the previous lecture. We have single source shortest path. In the single source shortest path, from one source we want to find the path to every other vertex, or you can say to every other destination. And for this we have discussed that Dijkstra algorithm is there. We have discussed the Bellman-Ford algorithm is there. Now all pair shortest path means we want to find out all possible combination in the given graph, and we want to find shortest path among them. What does it mean? It means if this is the graph given to you, something like this, so A, B, C, D are vertices. So we are interested to find out the shortest path among all possible vertices, means AB, AC, AD, BC, BD, BA, CA, CD. So it means all possible path we want to find out. And here very popular algorithm is Floyd-Warshall algorithm is there, and this is also based on dynamic programming. We can also use for constructing an optimal binary search tree. There are other problems can also be very much seen, like traveling salesman problem, where one salesman want to visit different cities in a minimum distance. So here also dynamic programming can be useful to give you the optimal result. Knapsack problem, we have discussed solving a greedy approach, and also we have realized that when you solve the problem by a greedy approach, then you don't get the optimal solution. You may get, you may not get, it is not guaranteed. But when we solve this knapsack problem with the dynamic programming, then the solution will always be optimal. Okay, so let us move to the next. So example, we'll take Fibonacci number is one of the example where we can realize its importance, that how it can be beneficial, or how it can be improved over the previous approaches. So Fibonacci numbers is a kind of sequence. For example, let's say our sequence starts from 0, then 0 1 means we have defined the first two numbers, and all the other numbers are derived by using these two numbers. So 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, then 8, then 13, and then 21, and so on. So this is our Fibonacci series, and we want to represent by using some logic. So this you can say that the first element is 0, so second is 1, and we can write a generic term that fn equals to fn minus 1 plus fn minus 2. So if you want to get the value of this, you need to look to the previous two terms and add it. So if you want the value of this, you just look to the previous two terms and add it, and you get the given term. So if we look to the top-down approach, we can see that we can represent this as f of n can be calling fn n minus 1, fn minus 2, then fn minus 2, fn minus 3, and so on. This is how we can represent our problem by calling it recursively. So let us look to this. For example, if I want to call f of 7, so f of 7 means it will call f of 6, f of 5, and this will call f of 5, f of 4, this will call f of 4, f of 3. Now when you call f of 2 and f of 1, it will stop. So this is a kind of exit point in our recursive call. So this will not call again because this is exit point. So this will call f of 2, f of 1. This is again not call, not call, not call. Now if you look at this, you can realize that actually to call f of 7, we need to make these many calls: 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 24. So these are the number of calls will be required to call f of 7. And if you want to represent this in terms of any recurrence relation, then we can also write t of n will be represented as t of n minus 1 plus t of n minus 2, and we are doing this with the help of some constant effort. So this is what we have already discussed, that how to represent any problem using a recurrence relation. And we can also write this as t of n should be more than equals to 2t n minus 2, and if we apply the master theorem, we will find that this is something 2 power n, so its running time will be exponential. It's very high, and space will be depending on the size, means we will see that how much is the stack will be required. So if you find out with the help of stack, you will find out that it requires only n memory cells. So in terms of space, it is big O of n, but in terms of time, it will be exponential, which is said to be a very time consuming algorithm, very costly algorithm. Now the same problem we'll try to solve by a dynamic approach using a bottom up approach. We'll see that what is the difference we will get. Okay, so first let us talk about this memoization idea, which is actually used in the dynamic programming, and then you will see that how this idea can help us to reduce the running time. So here we are referring memory space for storing the intermediate result, as we have discussed that in this approach we store the intermediate results. So memo is the term that we are using to refer to that memory area that will store our intermediate results. Fibonacci n, our interest is to find out the nth number of this Fibonacci series. So if n in memo, so this number is in memo, so we have to keep on storing the numbers that is actually available to us while solving our problem. If it is available in the memo, if this is existing in the memo, then we simply look to that index and get the answer. If n equals to 1, then f is 0. So we are assuming that our Fibonacci starts with 0. So we are provided with the two fundamental items, the first and second, and then the other items are, or you can say, can be derived by using the addition of the first and second. This is 1, this is 2, this is 3, 5, 8, and 13, and so on. So if n equals to 2, if it is element is second, then it is 1. Else we will be using n minus 1, means for any nth term we need to add the previous two term, n minus 1 and n minus 2, you have to add and you'll get it. And after finding the answer, you have to store this answer in the n. Now this we are doing when the nth is not already stored. If it is already stored, then you are doing this and you are returning from here. If it is not available, then you have to solve, and then you have to store this into the table and then return the f. So now this means only the first time when you are going to make a call, it has to execute, it has to do some effort, and later every time we are not doing any effort and we simply retrieve the results from this memo area, from this memory area, and can get our final result. What does it mean? It means, let's say if I am going to in the normal procedure, if I am going to represent f of 5, then this means f of 4, f of 3, f of 3, f of 2. Now if we don't use this idea of storing the intermediate result, then we have to call, means whenever you are working with f5, you have to call these many functions, right? Means for f4 again you have to make a call of these so many functions. For f3 you have to make so many functions. But if you look to this to this structure, and if you look to the nature of the function call, you will realize that while you are working with f5, now f5 initially is not stored in this memo table because we are not aware what is the value of f5, so it will make a call of f4. So you work for f4, and then it will recursively call f3, you work for f3, and then you recursively call f2, and f2 it is already known to you. So what you are doing, you are storing the result for f2, and then it will provide you the result of f3, then f4. Now what is the observation here? The observation here is it will only make one recursive call, and once you are able to get execute or put effort to solve any function, then you will going to store its resultant value. What does that mean? It means this f2, this f3, f2, f1, this entire function call will not be going to execute because already we have did the effort in the first call. and later call will simply be executed by looking to the table. So this is just we are looking for when f equals to 5. Similarly, you can imagine if the value is 12, then how much effort can be saved. So earlier when we were talking about this approach, the number of calls, or you can say the number of effort, will be something exponential, but now you can see that only you are going to make call for every number once at a time. That means it will require only big O of n, because all these call will be just a constant, because already the value is existing here. So we have realized here that from 2 power n we are able to reduce to big O of n, which is a big, very big achievement, or it's a huge reduction in the running time. So you can say in terms of efficiency, the time will be uh, linear, big O of n, and the space will be the same. So here we realize that the time is n and the space will be n. So we have got a huge advantage in terms of the running time from exponential to linear. So let us summarize what we have learned so far. So we can say that dynamic programming is basically requires two things. One is problem must be defined using subproblems, and the key idea is reusing these subproblems. So here we can say that you must be able to define a problem recursively, and also we can make use of memoization to avoid the uh, repeating calls of the same kind of problem. And with these two key ideas, by using recursive and memoization, we are able to solve our problem optimally. And one more thing that we can conclude is, because of this recursive and memoization approach, the running time can be defined in terms of the number of subproblems that we can see in the problem, and the cost of each of these subproblems. So you can say the time required for each of these subproblems. So normally we have seen that we have to solve each subproblems only once time. So it will take like big O of n time efforts and time for each subproblem, and each of these subproblems are actually stored in the memo area, in the memory area, and to access these already existing results will be of constant effort. So it will be big O of n. So this is what we have derived with this concept. So this is all the fundamental idea about the dynamic programming. So this is all for this lecture, and in the next lecture we are going to discuss more using some examples. Thank you very much.